for this first example of our chi-squared goodness of fit tests, what we're wondering is this die fair? If we built it out of this paper template and glued up the edges, do we make it fair instead of like waiting one number to come up more times than the other? So let's just give me your intuition. So what we would expect, right, if it's a fair die, is that all the proportions are the same. So that's going to kind of help us with our null hypothesis. Is like the statement of no difference. It's like they should be the same. We should expect 10 of each if we kept rolling 60 times. But what we observed, what actually happened, is you can see in the second column what we observed. So kind of eyeball those differences. Do you think, like, picture yourself rolling the die? Do you think the die is fair? Like, is that reasonable? So is the probability pretty good that you would get those, or was that like way out of the realm of possibility? What do you think? Okay, we'll hold that thought. We're gonna find out by doing a chi-squared goodness of fit test. And what the reason this is new is you might be thinking, well, we've already done proportions, right? But we only did a proportion of one thing. So let's, for example, a bag of M&Ms, right? If we want to know the proportion, say, of just red M&Ms, then we could do a test or an interval on that. And the bag would be our sample. And we want to know what the whole proportion is. So we already know how to do that. But what makes us different is it's the distribution of one variable. So there's lots of different categories. There's more than one category. You could roll a 1, 2, 3, 4, 5, 6. That's a categorical variable, right? These are all, everything in this unit is categorical. So we have to look at the whole distribution of just one variable. And that's why that's how you know chi-squared goodness of fit test. So what we do is for our null hypothesis H naught, if we defined let P sub n equal proportion of times, not probability, proportion you roll n, then we want P sub 1 to equal P sub 2 to equal ... P sub 6. So in other words, the proportion of each outcome rolled will be equal. It is another way you could write that. So P sub n, proportion of times you roll n, we want P sub 1 equal P sub 2 equal all the way to P sub 6. And then the alternative is that one or more of the proportions is not the same. One or more of proportions, if I can write, is not the same, because like it would only take one of them to be way off where we would say it's not a fair die, right? So we never rolled a 1 or something like that. Then that could affect the whole thing. So it only takes one proportion being way off to mess us up or to make us reject H naught. Okay, so there's something called a chi-square statistic. So it's not Z, it's not T, it's chi-squared, and it looks like this. It's like it's kind of squiggly X's, so it doesn't look like an X. It should have a curly X. So it's called chi-squared, not chi, like the T, not chi. So it's chi-squared. And the way you find it is you do get the formula on the formula card. It's the last one that we haven't seen yet at the bottom of the formula card. It's observed minus expected squared over expected. So it's like this. And it should make sense. It's 13 minus 10 squared over 10 plus, and then 11 minus 10 squared over 10. So we're trying to figure out how far away what we observe is from what we expect for each. And these are called components. and each component contributes to chi-squared. But like this one, what does this one contribute? When we rolled the fives, what does that equal? Yeah, it contributes nothing. So zero, it's possible for chi-squared to be zero. And that would mean everything is what we expect. Like it's all an equal distribution. And so the larger the component is, the further away we are from equality in that. So you do each component, and you can do them separately and write them down, or you can parenthesize really well. So let's see what each one contributes. By showing our steps, we can see which one is making chi-squared bigger. So this one is 0.9. You could do that in your head. This one is 0.1. You could probably do that in your head. This one is, when we rolled the threes, gives us a 1.6. That might be our biggest component. That's the furthest away. This one gives us a 0.4. This is 0, and this is 0.4. So we get a chi-squared of 3.4. So how unreasonable is that for chi-squared to be like that? And I'm going to show you what the shape of the distribution looks like in a second. But guess what? We can use our calculator to figure out the area under the curve. This is going to be a right skewed distribution, which you'll see in a second. And the mode will be equal to, you'll see why in a second, about 6 is the peak. So 3.4, I know this doesn't make sense why, but it'll be about there. So we're gonna get a good amount of probability. And the way you do it on your calculator is you do your p-value, right? Because p-value is area under the curve equals. And guess what? What do you think it's called to find the area under a chi-squared distribution? Yep. If you look on your calculator now, under distribution, there's a chi-squared CDF. And that, if you give it 3.4 or further away, you always go to the right for the chi-squared, because that's figuring out how far away you are from 0. Because if you got 0, that would mean it's definitely the same. And then you do give it the degrees of freedom, and the degrees of freedom are going to be a little bit different than before. It's going to be the number of categories minus 1. So the number of categories, right? There's 6 different outcomes. Those are the number of categories. And so it's 6 minus 1 is 5. So what do you get there? Okay, so if we round 0.664, 639, yeah. So that's a really good chance that you would get that outcome. So those of you that like nodded, yeah, that's reasonable. Yeah, it's definitely reasonable. There's a 64% chance that you could have gotten that outcome if we had a fair die. So we're definitely going to fail to reject H naught, right? So let me interpret this p-value for you. So it means, remember, it's always assuming the null hypothesis is true, which means if the die were fair. If the die were fair, there is a 64% chance we would get those results. There is a 64% chance we would get observed results, which is really, really good. So we fail to reject H naught. And then we do not have convincing evidence. We do not have convincing evidence the die is not fair. die is not fair. Does that mean we know the die is fair? Do we have evidence? Yeah, right. It doesn't mean this. So we don't have convincing evidence the die is not fair. That doesn't mean we know it's fair. We just know we can't say it's not fair. Okay, so that's